Thank you, everyone. And again, so this is Joe's work, and it's going to be Kelly's work. I didn't do anything on it. It's all their work. So hopefully I'll be able to be effective enough to present their amazing results. And if not, hopefully they forgive me. Joe having a family business with his brother getting married, and Kelly is serving cocktails in Yankton right now. So first thing we're going to start with Joe's. So Joe in our lab, in wet lab, he's working with multiple carbon nanotubes. But for simplicity, and you guys seen how computational works, so we need to make the model a little bit smaller. So he's working on single mold. So as we can see, here's the multiple carbon nanotubes. Here are the single or just one carbon nanotubes. And in order to look how the forms look like, I don't know, with help Dr. Keelan, I just drew this today. So this is, let's say this is, imagine this is a tube like that, or it can be different if we roll it the other way around. So it'll be different orientation. And the last one is a little bit twisted. So overall, there can be three different forms or orientations of the carbons on the carbon nanotube. So here's the model that Joe was working on. I assume he did this with Gauss View and did the computation with VASP. And also he used Molden. Let's hope the video works and see if shaking is going to happen. Yeah, there is some shaking happening. So the idea is he has a carbon nanotube like that, and he's functionalizing with different groups. Functionalizing means adding amines, NH2s, carboxylic, COHs. That's as far as I know. He's trying to add on the carbon nanotubes. So, as you know in computational, we're not just going to have a long tube and just keep on adding functional groups everywhere. Computation will take forever. So we're just going to take one unit, and Joe divided it into like 3 subunits. So every 3 rings, 1, 2, 3, there will be a 1 functional group. And then repeat the same thing pattern again. 3, then another functional group. So he did this, did the computation, and this, you guys are familiar with this, the spectrums. Here is transition energy, electron volts, I'm pretty sure. And here are in wavelength. Thing just for you guys, why do we report wavelength and we use transition energy? It seems like computational chemist more prefers the transition energy, but wet labs like us would prefer like wavelengths like this. And it's not like a general rule, but my observation is the spectrums will be the same. This one will be the same as this one, but flipped the other way around. Someone will ask me, this is way different than that. Kind of. This window here is around from 2.5 to 6.5. If you flip it around, you will get this. Okay? And here is the UV vis. I assume they split the spectrum from 0 to 3000, going really high numbers here. And here's just from 200 or just 0, 700, just because this is probably the most interesting one that scientists, wet labs will be interested in, which is the UV vis range. So here's the continuation of what he did is calculation of 3 periodic unit cells. I showed you like 3 benzene, every 3 benzene rings, there will be a functional group. And he did the calculation, 360 states with nearly 1,000 lines in oscillator strength. So oscillator strength is dimensional quantity that would express the probability of emission. Sure, that would express the probability of emission or absorption. So any of those spectrums that you see is just using this oscillator strength. But the problem is using 3 units, as you can see, it was like taking forever from him to compute, and it's going to take a long time. So he decided to make it on a smaller scale. So he decided to use on every 2 benzene rings, you would have a functional group, just a smaller pattern. The other thing he will consider in the future is if you're going to add different functional groups. So this one is just a very small functionalization. I assume it was 1,3 cycle addition by glycine and formaldehyde. In the future, if he's going to use bigger or longer linkers, maybe it will be attached from one carbon here to a carbon here. So this will be long, yes, but the pattern of repetition might be shorter in distance. Things we're going to have to consider in the future. So K points. K points, this represent the momentum of the orbital, molecular orbital. So let's just say it in a simpler rule. Increase the K points, you will be able to see the momentum, not the right word to say, but the density of the momentum of the orbitals moving better. So more K points, more better calculation. Okay, lower is not that great. So here are the next 3 slides. I'm going to go quickly through them. So here's the calculation based on only 4 points. 1, 2, 3, 4. So just only 4. Here is based on 8. 16, something funny happened with the calculation. It should be better, but it didn't really come out this way. So this one looks better. So if you have 8, you will get better understanding of the momentum. And as you can see, electron increases here. This is more representing to the electrons. These are holes. So the higher you increase the momentum, there is an equation for it. The higher you increase the momentum, the higher the energy. And the holes is the other way around, because it's the other value around. So that's Joe's work, and he thanks Dr. Keelan. He thanks Wendy and Adam. And he thanked you all, and he also thanked me. And special thanks for his dog, Mocha. And yeah, that's her. Do you have any questions for him?
Okay, let's thank Khaled and Joe for the presentation.